In this section, we're talking rational exponents. The goal is to simplify radical expressions using rational exponents. Okay, rational is another name for fraction. When you see rational, think fraction. So in this section, I'm going to remind you what it means to have an exponent that's a fraction. So definition, a to the 1 over n, so that's an exponent, a to the 1 over n, is equal to, well, we've already talked about it a little bit. Do you guys remember? It's the nth root. It's another notation for the nth root of a. A to the 1 over n is equal to the nth root of a. And the reason we use that notation is it works. With the laws of exponents, as you'll see, it works. Now, if n is even, what do we have to assume? At least for now. We have to assume a is greater than or equal to 0 because if n is 2, we're not going to take the square root of a negative number, are we? The answer is non-real if you do that. So if a is greater than 0, we'll assume n is even. I'm sorry, other way around. If n is even, we'll assume a is greater than or equal to 0. Okay, so simplify. Before you just give me the answer, can you rewrite in part A 49 to the 1/2 in root form, in radical form? What does 49 to the 1/2 mean according to that above definition? Yep. And then you guys all know the square root of 49 is 7. Now here's one in part B. What do you suppose we mean by this notation? The negative 27 to the 1/3. I'm going to write down two notations. You tell me which one's correct. Do we mean the cubed root of negative 27, or do we mean the opposite of the cubed root of 27? What's that? Good. The second one. When would it be this first notation? You'd have to have parentheses around the negative 27 for it to be the first one. Does everybody see the difference? That's an important, subtle thing that you could easily make a mistake on. So I'm not going to erase it. I'm going to cross it out to keep it in your mind. That is not what this notation means. Okay, what's the opposite of the cubed root of 27? Yeah, the cubed root of 27 is 3. You're just taking the opposite of 3. Now, by the way, what if we did write down in parentheses the negative 27, and then we say, oh, that's the cubed root of negative 27. What would the answer be? It's an odd index. So the answer would actually be the same, wouldn't it? It would actually be negative 3. The same. But the notation is definitely does not imply the same thing. You do get the same answer in this case. If this were a 1/4 or a 1/2, and you had the negative number in parentheses, then it would be a non-real answer. So if you had negative 4 in parentheses to the 1/2, that would be the square root of negative 4, non-real. Right? We don't know how to take the square root of a negative number yet, or we're pretending like we don't. If you've seen it in another class, just go with it, pretend. So in this case, it's non-real, whereas, so I'm kind of doing separate little examples here. If we wrote it without the parentheses, what would that mean? Yeah, it'd be the opposite of the square root of 4, which is the opposite of 2. So you definitely would not get the same answers if you had an even index, an even root. So subtle things with notations that you got to pick up on, or you'll make mistakes and potentially get wrong answers. Okay, so you've probably seen that fractional exponent notation before, but maybe you haven't seen this one. In this one, we're going to extend that definition. We're going to extend it to the definition of a to the m over n. So now the numerator of that exponent's not 1 anymore. And here's what this equals. A to the m over n power. There's two ways to think of it, and they're equivalent. So just like before, a to the 1 over n, the 1 over n, if you look at that, so let me write it down separately. A to the 1 over n equals the nth root of a. The index of the root is indicated by the denominator of the exponent, isn't it? And that's going to be consistent with the new definition. The index of the root is going to be the denominator of the exponent. So this is going to be the nth root. And then m is going to be the power on the a. The nth root of a to the m. However, you can write it with the m on the outside. You'll get the same number. It doesn't matter if you take roots first and then take powers, or take powers first and then roots. You get the same thing. So you could just as easily write it this way. The nth root of a, the whole thing to the m power. Bring the m on the outside. Now, if you're not using a calculator, it's often easier to use take the root first, because you get a smaller number to the m power if you take the root first. So let's look at some examples. Let's simplify 8 to the 4/3 power. Okay, first let's use the definition and write that 8 to the 4/3 power in radical form. So this is in rational exponent form. Let's write it in radical form. So what would, according to that definition, what would 8 to the 4/3 be in radical form? So what was the index? So the third root of 8 to the 4th. The third root of 8 to the 4th. Or it could be the third root. Equivalently, you could have the third root of 8 brought to the 4th power. Those are the same number, but which one, if you have to compute it by hand, which one do you want to compute? I'd want to do the right-hand one first. You guys see why? Isn't it easier to take the 8th root, or the third root of 8, than to take the third root of 8 to the 4th? Which one can you do? Which one do you have a chance of doing in your head? The second one, right? It's easier to do the root first. So I think we can actually do this in our heads. What's the cubed root of 8? 2 to the 4th power? 16. Yep, we can do it in our heads. But could you do the cubed root of 8 to the 4th? Could you take 8 to the 4th in your head? No. So the first way, although it's true, if you could do this on your calculator, it's true, but you don't want to do that, right? What about, let's do something similar for 81 to the 3/4, yeah. No, you would get the same answer. It's just harder for our minds to do work with big numbers in our heads. And that's what you'd get if you took 8 to the 4th first, right? Because with this notation, think about how you compute this. When it's written this way, it's telling you to compute 8 to the 4th first. You work from the inside out, right, with this notation. I don't know what 8 to the 4th is off the top of my head, do you? If you do, more power to you. But then that's a big number, and I don't know what the cubed root of that number is going to be. So no, it is going to be 16 overall, but getting there would be harder. It'd be a harder road to travel. So I wouldn't do it. Let's do something similar with 81 to the 3/4. What do you get when you transfer it to radical form? Yeah, two ways to write it. The 4th root of 81 to the 3rd power. So remember, the denominator is the index of the root, and the numerator of the exponent is the power. But that would be hard to compute, wouldn't it? 81 cubed, 81 times 81 times 81. I don't want to do that if I don't have to. So the other possibility that we could probably more easily compute, what's another way to write this thing? The 4th root of just 81 to the third power. Okay? I think I can do that one in my head. What's the fourth root of 81? 3. And then you still have so it's like I don't need those parentheses anymore, but that's what I get when I take the fourth root of 81. Remember, you do it from the inside out. And then what's 3 cubed? That 3 sticks around. So 27.